Model Guidance for Adaptation Planning. Is CMIP the way forward? This is a talk given in June of 2022 at the Actionable Science and CESM session of the CESM annual meeting. Thank you for asking me to give this talk. I will be representing and expanding upon work that I've done with Laura Briley over the last decade. Laura has made consequential and unique contributions to the usability of climate simulations in adaptation applications. Today I am going to explore the question of whether CMIP is the way forward to provide model information for climate adaptation. CMIP, the Coupled Model Intercomparison Project, has been and is one of the most important parts of the climate science community. It has promoted controlled experimentation and supported a culture of extraordinary evaluation. CMIP is at the foundation of us having historically unique knowledge of our future, which gives humanity the opportunity to affect our future in ways to establish positive outcomes. I will make a case here that CMIP simulations are not the right type of simulations for adaptation planning. To frame my argument, here are some starting points. First are the terms useful and usable. Scientists often maintain that they are providing research and products that are useful. There is another point of view, that of the user or the practitioner. It is the practitioner who defines ultimately usability. Our research in GLISA, the Great Lakes Integrated Sciences and Assessment Center, investigates the gaps between scientists' notions of useful, what has proved to be usable, and how to build the connections, the knowledge system, between knowledge providers and users. Next, I will define some terms. A good starting point is the work of Cash et al. 2003. Who defined the terms legitimacy, credibility, and salience as attributes that knowledge needs to have to be usable. Legitimacy is an attribute of objectivity, fairness, and a lack of political bias. Credibility is an attribute of scientific adequacy. Salience requires that information be relevant to the problem to be addressed. Many scientists have sought to address the challenges of salience of climate models by bias adjustment, downscaling, and calculation of indices. In this talk, I will focus more on credibility. In addition to Cash et al.'s attributes of knowledge, we have added plausible and ethical. By plausible, we seek to assure that scenarios used for planning and decision-making are physically consistent or realizable. Recognizing that climate change does not lead to a single outcome, we seek to steer planning away from probable futures to a set of plausible futures. By ethical, we recognize the issues of equity and social justice. We also recognize the responsibility of scientists to describe and represent uncertainty in a way that neither understates nor overstates what we know. All of these attributes, legitimacy, credibility, salience, plausible, and ethical, are to build trust with those participating in a particular adaptation problem to be addressed. The final framing point is to examine how models are, in practice, used to develop reliable scenarios. A good lesson is from weather forecasting. Global weather models have many similarities with global climate models and historically were construed to provide deterministic forecasts. That is, this is what will happen. Increasingly, model simulations are viewed as probabilistic, not deterministic, and provided by well-designed ensembles. Professional weather forecasters do not view the models as providing the forecasts. The models provide guidance to be used in combination with other sources of information to provide forecasts. These other sources of information include a portfolio of models designed for different purposes, For example, models to characterize known uncertainties in global models, as well as regional and local details of the forecast target. The model guidance is used in concert with observational information, underlying physical theory, and very importantly, expert interpretation to provide forecasts and accompanying descriptions of uncertainty. Now I want to turn attention to applying model information to adaptation problems in the Laurentian Great Lakes, Lake Superior, Michigan Huron, Erie, and Ontario. Our experience in adaptation applications is that practitioners are attuned to local weather. They are especially interested in their community's vulnerabilities. In fact, they are often motivated to think about climate change by some weather-related event, such as a flood. These vulnerabilities leave them highly focused on weather events. They want to know how things have changed locally. Once they frame their problem in terms of a real-world issue of direct relevance to them, then we can talk about the future. What we can say about that future comes first and foremost from model simulations and primarily CMIP models. The questions arise: is the information from the models salient? Are the models credible? Again, credibility is an attribute of scientific adequacy, and in this case, adequacy for their adaptation application. Let's consider some of the issues of model credibility. I want to start with the ubiquitous problem of credibility bias. Bias is a pervasive problem in our models. We have purported to make climate simulations more salient with bias correction. This, however, is not a correction. It is an ad hoc adjustment. If we look at the adjustment on a scale even as large as the Great Lakes, these adjustments are large. Not only are they large, the seasonal variability and the relative balance of the physical processes are not defensible. Large bias adjustments to tailor the simulations to make them salient make them non-credible. We have calculated the bias of 65 models, including CMIP models, North America Cortex models, and the University of Wisconsin models that are our primary modeling tool we use at GLESA. Shown in this figure are biases by season of precipitation from -50% to +50% and temperature from -5 centigrade to +5 centigrade. White is unbiased and darker colors are more biased. The next figure takes the worst season from each model and places them in a table with temperature bias along the top columns and precipitation bias along the side rows. If we were to select an ensemble of models with less than 2 degrees temperature bias and less than 25% precipitation bias, then we would have 3 models in the ensemble. 5 of the models do not even make it into an ensemble if we allowed 5-degree temperature bias and 100% precipitation bias. Bias in important quantities, such as net basin supply to determine water levels, is frequently greater than 100% and varies month by month. We find it both more plausible and ethical to interrogate the information in the unadjusted simulations. Above, I mentioned that local practitioners are attuned to weather. They know that summertime flooding events at the Great Lakes come in organized storms and often in mesoscale convective complexes. Windstorms come in severe thunderstorms, derechos, and tornadoes. Global climate models do not represent these events. Regional climate models cannot credibly generate them from the flawed boundary conditions of global models. A central part of our evaluation of model credibility for adaptation is the representation of weather features. Some weather events are represented well, others not at all, which contributes to seasonally varying uncertainty analysis that are difficult to reconcile. Finally, I will introduce a fundamental structural element. Are the Great Lakes represented in the models? It is difficult to talk to city officials who live in the lake effect rain and snow bands and say that a climate model does not simulate a lake effect. It is even worse to confess that a model does not even have a lake. It is perhaps embarrassing to say, yes, there is a lake, and the surface temperature of the lake is determined by interpolation of the sea surface temperature between the Atlantic and Pacific Oceans. The Great Lakes, more generally local details, must be present in any credible model used to provide guidance for adaptation applications in the Great Lakes region. The overhead of determining the representation of the Great Lakes in CMIP models is far too large. We started looking for information on the representation of lakes in CMIP 3 models prior to 2015. Then we had to start over with CMIP 5 models. Ultimately, we developed a decision tree algorithm to determine the potential of models to be credible. It took us more than 4 years. We do not have the right approach for providing information that we need for decision making. Models are built for purpose. Those of us using CMIP simulations and adaptation planning are using models that were not designed for that purpose. Good practice of the science of modeling tells us that we need model guidance designed for the purpose of adaptation. CMIP models were built for understanding. By comparison, models used to provide guidance for weather forecasting have quite narrow purpose. They are designed to define information on different time spans at different spatial scales. They are focused on physical processes of specific phenomena and vulnerabilities. I note that there is a great amount of understanding that follows from evaluating models designed for specific purposes. We need models that are designed for adaptation applications. We need models documented for adaptation applications. I see some jumping to the conclusion that this is just a decadal prediction model. I do not want to equate the need for adaptation models with the need for decadal prediction. We can undertake credible decadal prediction and ignore the Laurentian Great Lakes, sea level rise in Charleston, South Carolina, and fail to generate the knowledge base needed for adaptation. I assert that this global modeling capacity is not best achieved by increasing resolution, complexity, and comprehensiveness. These adaptation models are not the CMIP models, and they are not rationally incorporated into the CMIP organization. That said, within the portfolio of models needed for adaptation, we will need global models. But we need to think broadly and consider the design of suites of models needed to address gaps in the global model and to contribute to the uncertainty description. We will benefit from thinking of the optimal interface between global information and other sources of process and local information needed for specific adaptation applications. Such a modeling capacity addresses environmental, economic, personal, and national security. Two obvious critical and urgent needs are models to address sea level rise on decadal time spans and geoengineering. The design of this capability requires knowing how model guidance is used by practitioners and how scientists can contribute to the interpretation of climate knowledge in context with other factors that planners and decision makers must consider. Thank you for your attention.